Okay, last time we were talking about sway, and I said we will continue with the main topic because the column slenderness is very complicated and too many things have to be considered if you want to include the slenderness of the column in the calculation. And it depends on so many factors. As I mentioned to you, the problem is with the stiffness because the slenderness issue is related to deflection, and deflection is related to stiffness, stiffness is related to cracking, and also related to nonlinear stress-strain curve. So it's a very complicated problem, and it cannot be actually solved easily because moment magnification in one column causes moment magnification in beams also, and that causes there and there, so it both spreads away. So it's not just one column problem. This is a problem which affects the whole structure. So if you have a slender column, then that slender column will affect the analysis of the entire structure. So it's a complicated problem which is very hard to solve accurately. And that is why I mentioned that codes have come up with a easier way to do that, which is moment magnifier method, and I will discuss that today from two codes, ACI and British. So first of all, the moment magnifier method tries to account for all of these things. An approximate method to account for slenderness may be used instead of P delta. P delta analysis is a more refined analysis in which we take into account the deformation and load effects simultaneously. And this is done for the whole structure called P delta analysis. And P delta analysis can be done by more advanced programs that have capability to do nonlinear geometric as well as material nonlinearity. And many programs do not have that capability. And even if you do have the capability for steel frames, it is easy. For concrete, it is very difficult. So because this is too difficult, we can use this method as long as KL over R is not more than 100. K is the effective length factor, which can be anywhere between 0.5 to infinity, as I mentioned to you last time. L is the length of the column, and R is the radius of gyration. What is the radius of gyration? What is radius of gyration? What is this property called radius of gyration? How can we calculate it? I by A? Okay. Yeah, this is actually trying to govern the area of or the center of the section, which when bending occurs, no tension occurs. So it's that load, if there's within that area, then that zone, that it tries to get that width of the column in which if you put the load, it will not cause tension generally. So that radius of gyration is put here, and normally it is 0.3 of the cross-section size for rectangular, 0.25 for circular, and so on. So you divide that. If it is more than that, then you cannot use approximate method. You must use P delta. So engineers who are lazy, what will they do? They will make the column big enough so KL over R is never more than 100, so they never have to use P delta analysis. That's one way to solve the problem. Don't make the column too slender, then you don't have to use the analysis. But sometimes it's not possible. Sometimes the architects and other considerations require very slender columns. So we have to use P delta in many cases. Separate, so now this is very important. Separate magnification for sway and non-sway cases. Because for non-sway cases, because the column cannot sway, so K is between 1 and 0.5. And sway cases, K is between 1 and infinity. So totally different cases. That's why the moment magnification is calculated separately. Normally we call it small delta and large delta effects. Small delta effects, which is the raised column magnification, and large delta, which is the sway portion. So these two are treated separately. Moment magnification generally is between 1.2 to 2.5 times. Of course, it can be more, but it's not good to have a column in that range. If the magnification is more than 2.5, you better change the column or the framing because it's too much. mostly suitable for building columns, not so suitable for bridges and other places where P delta is more important. So this is the moment magnification factor. Now, the design moment, if you remember, I showed you a slide that from the analysis moment that you get from the frame analysis or from ETABS or simple analysis, you need to calculate the design moment. So this is the design moment, and this is calculated by two factors. Moment, which is non-sway part of the moment, multiplied by non-sway factor, and sway part of the moment multiplied by sway factor. So what does it mean? What is the non-sway moment? What do you think? What is the non-sway moment? Moment from a load which does not cause sway, like dead load, gravity load, because it doesn't cause the building to move left or right. So that moment will come here, and that will be multiplied by non-sway magnification. And the sway part, which is the earthquake or wind, will be multiplied by sway magnification, and then these will be added together. Before 1977, there was only one factor, and then after that they separated into two factors. Now, how do you calculate these things? So this is the larger sway moment because column has two moments, top and bottom, right? So out of those two moments, the larger of the two is taken in this case. Larger of the non-sway moment, so because there are two moments in the column, top and bottom, so you take larger of the two moments. This is the final design moment. This is magnification of moments that do not cause sway, and that is magnification of moments that cause sway. So it's very clear. Now, how do we calculate these two factors? That is the next question. So basic idea, let's talk about non-sway factor first. So non-sway factor delta is calculated by using this equation. CM, you remember CM, the moment shape factor? I can see blank faces, they have no idea what was CM. We discussed about CM so much. I said CM is between 1 and 0.4, it depends on the shape of the moment. Why it depends on the shape of the moment? Because moment is the one which is causing the deflection. So shape of the moment diagram is important. So CM is a moment shape factor, right? Please remember that. And then PU is the ultimate load on the column, factor ultimate load on the column, and 1 minus 0.75 PC. PC is the critical buckling load. So if you calculate that, you should be able to calculate that one. Moment curvature coefficient, applied load, and critical buckling load. And critical buckling load is equal to pi square EI over this one. What is this called? Anybody knows the name? Euler. Right, Euler load. Mr. Euler is the one who derived this equation. Now, seems like an easy enough equation, this one. What is the problem here? K and yes, always. Because these for concrete, reinforced concrete, our topic, EI is not easy to calculate. And K is also not easy to calculate because K has too many complications that we discussed earlier already. So calculating PC is actually quite tough, because it involves many things. Of course, codes have simplified EI calculation, I showed you last time. Also K equations have been given, so you can use the simplified equations, but they are only simplified. In any case, we can use PC, we can put it here, we can calculate the delta NS. So delta NS can be calculated, but as you can see, it must be calculated for each load case. And PU corresponding to the moment that you are considering, because this is a non-sway case multiplied by non-sway moment. So it must correspond to the same load which is for that load combination. So there are some fine points when you apply these equations, which PU to take. So one load combination must be taken. A combination that is not causing sway. Effective length, flexural stiffness, so we do that. Then we go to sway factor, right? Sway factor is calculated by this equation, 1 over 1 minus q, and must be more than 1, where q is that, and this is a good equation. This is a better equation than previous codes. Previous codes, the equations were very complicated. This quotient, sway quotient, basically is trying to estimate what is the level of the relative displacement in the column to calculate the capital delta effect. And you can see here PU delta naught, VU LC. So, and the problem is this guy, sigma. It is saying that you must add all of the load in the entire story because the entire floor can only move together. Each column cannot move independently. And because this is a sway related magnification, so all columns must have the same sway at one time. The other delta will be individual because it is based on individual loading and individual curvature. This is global curvature of the floor, so it must be based on the entire floor. So that is why the PU of all the columns in a floor must be added together. And then the total story shear, total floor on horizontal floor, on the horizontal load on the floor, delta naught and LC. If this delta S comes out to be more than 1.5, then you have to use this equation, which is not good because then you have to calculate the PC of all the columns in the floor. Imagine 100 columns and you have to calculate the critical buckling load of 100 columns and PU and then calculate this one. It doesn't get easier at all, right? And again, then engineers try to be within that range. If it is more than 1, they change the column. Don't want to go there. But the point I'm trying to say is that even the simple method is actually very complicated when you apply it, because hundreds of load combination, this must be done for each load combination, not once. And it must be done in two directions. First in X direction, then in Y direction. All the load combinations in Y direction, all the load combinations in X direction. And each load combination must be decided whether it's a sway combination or a non-sway combination, so that we can use the appropriate way to do that. And that is why this whole thing becomes a bit complicated. Alright, so basically the idea is that we try to estimate the moment magnification of the columns using the simplified procedures, which are partly based on analysis and partly based on the Euler's theorem. So sum of column loads, relative displacement, story height, story shear, sum of shear to column as I mentioned to you. So you can see from there, and PC is like that, flexural stiffness. So now we have a complete picture of the entire procedure on one slide, right? Everything. That is the equation, line moment, that one is that one, that one is that one, that one is that one. So everything is there, right? So make sure that you understand the concept behind the equations from the code. So that is the ACI code. And this is one of the best one amongst all the codes. The moment magnification of ACI is one of the best one in terms of it tries to include all the important factors. So importance of now this is a very interesting question. Why column slenderness is a more serious problem in short building than tall buildings. There are many reasons. This is very important because this will also tell you why slenderness is important. First of all, for tall buildings, I will tell you why it is not important. Tall buildings, the column size is very large because the axial load is very high. So the column size is like 1 meter or 1.2 meter or 1 meter by 1 meter. Story height is the same whether it's a tall building or a short building, which means that for a tall building, the KL over R will be very, very small because 3 meter column, 3 meter height, 1 meter column, it cannot be slender. It is just too big to be slender. For a 2-story building, the column size will be maybe 200 millimeter or 300 millimeter by 300 millimeter for the same 3 meter height. So obviously the column is likely to be slender because it's too small, because this building load is too small, so people make the column very small, sometimes only 250 millimeter, 25 centimeter or even smaller. So it becomes a problem. Second is that normally for tall buildings we have big shear walls, elevator walls, which prevent the building from swaying. So buildings become non-sway because the shear walls control the sway. Big shear walls or big elevator walls do not let the building move too much between two floors. So the sway between two floors is very small. 3. For small buildings, especially on the ground floor, the height tends to be high because they have sometimes the foundation is below, there are missing ground beams, and also for the ground floor, they tend to make higher floors for mezzanines and so on. So for short buildings, actually the problem gets very, very severe. And if we miss that, then we are in a danger of column failing first. Another issue is that Mr. Ong might have told you that one of the important factors is that the columns must be stronger than the beam, right? But in a small building, it's impossible to do that because this is the span. Let's say it's a tall building, 7 meter span. In that case, the column will be 1 meter by 1 meter, beam may be 0.7 or 0.8, so the column will be stronger than the beam in any case. Same span, short building, beam will be the same, 0.8 meter, 0.7 meter, and column will be now only 0.3 meter. So now the column will become weak because the span is the same, but the column size has become smaller because the load is small. So everything is going against the small buildings. And the engineers who are designing small buildings or short buildings, they think that they don't need to worry about these things because they are just only doing 2-story building. And that is why I think every earthquake, every time, what gets damaged? Have you ever seen a tall building falling down in an earthquake? Never. Always 2-story buildings, 3-story buildings, they are the ones that get demolished most often because of these things. First of all, there are many other reasons, irregularity and so, this is one, and people do not pay attention to them. So if you are going to be a structural engineer, do not underestimate 2-story building, just thinking, oh, it's 2-story building, I don't need to care about that. That is the one that you need to care much more than the tall building. All right? Now this is a parametric study. What happens if you change the column size and slenderness? How does it affect the slenderness? So we have a column 30, 40 and 80. I'm showing you the difference between short and tall building now. This is a small building, this is a big building, tall building, right? And you can see here that if you look at that, so this is the load range. So load will be varying between this, so we'll check the load here. That is the length, that is the framing. So we use a program called CSI call for this, which I also developed. I cannot share that with you because it's still locked, license is locked. So it is using that program, we calculated you can also use gear to do the same study, right? So we try to see what is the effect of those parameters. And then beam, this is the data. So from the presentation, you can use this data if you want to use gear. And then we vary the KL over R. You can vary the height or length. So we vary the KL over R from 14 until 57 to study the effect of KL over R on the moment magnification, just to develop understanding of how these things work. And then we found that this is the moment magnification. So P versus PU or P naught in that range, and then moment magnification. And we found that moment magnification ranges maximum to, as I mentioned, 2.5. So even in worst cases, when the column is very long and the load is very high, still the moment magnification reaches about 2.5, does not cross that. So that is why I gave you the range that moment magnification typically stays, most normal cases it will stay under 2 if you are in that range, right? KL over R, this one and this one, so it will remain under 2. So this is a good study to understand how much is the range of the moment magnification, even if you change the parameters quite a bit. Very heavy loads and very long columns, but still, but this is, the important thing is here. A certain point of KL over R, then this becomes very unstable. So you need to stay away from that range. If you go to that column size, KL over R, it starts to become readily unstable. And this is, you can see, if I use one more KL over R, it will go like this. It will become very unstable very quickly. So there is a stable range, and then there is an unstable range. So if you tend to stay in this stable range, so KL over R around this one up to here, 47. So around that one, it's 50, 57 is fine. Beyond that, then it will become unstable. So that's just a parameter study that you could also do by yourself. And then another column, same thing. For bigger columns, the maximum moment magnification is now less, 1.5. And then the biggest column, we change that and it's only 1.0. So this is the tall building case. For tall building, even the worst one with a bigger column and that one, the moment magnification hardly crosses 1. Right? So that's the lesson from this one. The bigger columns for a typical tall building, moment magnification will be quite small. And for small columns, it could be quite large for a shorter building. All right. So this is the procedure, step by step, that I mentioned to you. You can read this. I don't need to repeat that. So your assignment you will do following this procedure. Okay. Step 1, step 2, step 3. That is the diagram that I made over there. So it explains PU1, PU sum, the diagrams over there. So you can see from there. Now let's go to the advanced method, P delta effect. If you cannot or you don't want to use the approximate method, you should know something about the advanced techniques also, the true techniques, so to speak, P delta. So P delta analysis, SAP 2000. How many people are familiar with this program? How many? 3, 4, 5. Okay. So that program and many other programs have the capability to do P delta analysis, and P delta analysis is analysis which considers the incremental increase in moments due to the axial load. And it does that in steps. So the load is applied in steps, the deflection is calculated, next step, the deflection is added, moment due to deflection is added to the next step. So it's a iterative procedure. So Also, you should remember P delta and buckling is not the same. Okay, what is buckling? The other load, PC. What does it mean, buckling? Can somebody tell me the phenomena of buckling and the difference between buckling and P delta? Let's say this is a column, right? So, slender column. So, if I apply load, this will do like that, right? What is this? And where is the P delta? Not necessarily. You see, the thing is that buckling is related to geometry. P delta is related to forces. P delta means that the moment in the column will increase because of the load and the deflection. So the total moment will increase in the middle. When I apply this load, deflection will increase, and deflection will increase the eccentricity of this load. Constant load, the moment is increasing. But buckling means that it will continue to carry the load, but the deformation will be so large that it will become unstable. So suddenly, this is too flexible, but normally what happens is that the structure will continue to carry the load, straight member, and suddenly it will fail. Not fail, it is not called failure. Suddenly it will deform a lot, but will continue to carry that load. This is very important. Buckling means that the structure will buckle, but the load carrying capacity will not reduce. Large deformation will happen, but the same load will be carried and then it may fail in other modes. So buckling itself does not mean that it loses the capacity to carry the load. So buckling is initiated suddenly with no deflection before buckling and no moment before buckling. P delta is that there is a deflection due to load right from the beginning, which increases progressively until it reaches failure, right? So buckling is a theoretical concept. It assumes the column to be perfectly straight and load applied perfectly in the center. Only then buckling has any meaning. Practically, buckling does not occur. Practically, P delta effect occurs because columns are never perfectly straight. So when you apply the load, they always have a little bit of moment, or the load is applied slightly off center. Because how can you apply the load in the center? There's no such thing as a point load. You don't have a point load. You have the beam coming here, beam is connected, beam is causing bending. So in all cases, column is subjected to bending. So if the column has bending or eccentric load, which is the same thing, you will have P delta. But if you have zero eccentricity, perfectly straight column, you could have buckling, right? So buckling is a theoretical number. So this is the typical failure in column. You can see from here many reasons: ties broken, ties breaking, crushing of concrete, local buckling, the plates. This is the lateral buckling of the steel section inside the column, buckling of the rebars. This is the buckling of the bars that causes failure. So we need to prevent that. So that is the buckling analysis. So basically, I was saying we assume that the beam is perfectly elastic and straight and it's no moment, but at some point it will suddenly deflect. So we can calculate that sudden deflection by assuming there's a spring holding it in the middle, and then that spring stiffness is actually used to calculate the buckling load, which is holding it in place. So that analogy can be used to calculate the buckling loads. So if it deforms, then that will be the force required to deform, and from that the reverse calculation for the buckling can be done. So this is the explanation of that critical buckling load, the one that we talked about. And bifurcation, the one that I showed you. So that is the bifurcation point. So it goes like this, and after that, suddenly there will be the bifurcation means that you suddenly direction of the displacement changes rapidly. So it's a bifurcation point, that means, and we don't know. Actually, the interesting thing is that for a circular column, we don't know which direction the buckling will happen, because it's a stiffness the same in all directions. For a beam, rectangular section, we know it will happen in the weaker direction first, but we don't know left or right, right? So deflection can be negative or positive. But for a circular column, we have no idea where the deflection will happen. So deflection can happen in any of the directions. So that means if you plot a deflection, depending upon which deflection you are plotting, you may not see the buckling. So that is an interesting part, because the buckling can happen in many directions, and it can go suddenly. So bifurcation point means that we don't know what will happen at that point. There is also a phenomenon called snap-through buckling, which, okay, I don't want to complicate too many things. So as I mentioned, no column is really straight. So in reality, we have P delta. We don't have buckling. So that is the pin supported column, various configurations. Just like buckling. Okay, buckling. Yeah, that's important thing. Buckling has many forms. Buckling modes, we call them buckling modes, just like the dynamic modes of a vibration, right? We have the same case in buckling. So this is just like a dynamic mode shape. We have a buckling. This is the first mode buckling. So this has the smallest load associated with that. If you prevent that and you put a pin here, then the second buckling mode will be activated, which is higher load. And then if you prevent that also, third buckling mode will activate at a higher load. Just similar to the mode shapes of dynamic mode shapes of a structure, that if you have the first mode with a frequency which is, the initial period is largest, and then second mode smallest, and so on. So it's the same concept in buckling. It's the same. In fact, the problem is mathematically it's the same problem. You try to calculate the eigenvalues of the problem, and those eigenvalues give you the buckling modes. So the buckling analysis and modular analysis mathematically are same problem. So it gives you the idea about buckling. This is something to do with buckling and yielding. So effective length, summary, L, you have already shown you. Then comes P delta, which I explained to you, and second order analysis. So this is called second order. P delta is normally called second order analysis. That means first order means only consider that the structure is straight and it remains, for the purpose of analysis, the structure remains straight and we calculate the deflections. Second order is that you apply the load and the structure becomes deformed, and the deformed structure is used for applying the next load. So it's a second order. So we have talked about it, magnification of axial load, slenderness of the structure as a whole, slenderness of individual members. So just an explanation of what we already talked about. By controlling slenderness, the magnitude of the P delta effect is often managed, right? As I mentioned, I showed you P delta effect. KL over R is the key. So if you want to reduce P delta effects or moment magnification, you reduce the KL over R. I showed you some examples. And sometimes it becomes so small that it can be ignored, right? So if you keep it small enough, like 5%, 10% moment magnification, then you can ignore it. Normally 5 to 10% moment magnification, we ignore it. So if we try to keep the structure so stiff, then we do not have that problem. So P delta, small P delta, large delta. So small is related to the local buckling, local deformation, non-sway case, and that is the sway case, right? So it's just explanation of whatever I have shown you before. So this is normally called large P delta, and this is called small delta. Thanks. So P big delta and P little delta, right? This is P and S in ACI code. This is PS in ACI code, but they are the same in concept. And this is no explanation of how the building sways, and that is the delta, that is the horizontal force. So you calculate based on the data reflection of the entire floor. And that is why in the design of buildings, the most important control is sway. So that is explanation about the two deltas. Please read this. Yeah, this is what I was talking about, the acceleration response corresponding to. So sway is related to if it is too much sway, you have to go too far, acceleration will be very high. So people will feel it, right? So that's why it needs to be limited. So acceleration of the building, moving, speed, velocity and acceleration, and also the amount of display, they need to be controlled. In fact, this is one of the key control in building design is sway. Everything ultimately comes down to sway control. If you can control the sway, everything else will be controlled. Building will not fall down if the sway is limited, because building only falls down when sway is large. A straight building, unless something really bad happens and the column axial capacity was not enough, it should not fall down, right? So sway control is important, and that controls slenderness, it controls the moment magnification, it controls buckling, it controls everything. All right? Any questions about column and slenderness? Anything that you did not understand, please ask me now as a concept. So let's conclude. For column design, we have to worry about the capacity of the section, which we can calculate based on the theory that we developed, the equation, interaction diagram. So that gives us the capacity of the section, not of the column. To get the capacity of the column, we need to add the slenderness into the moments that we use for the section capacity. So section moments need to be increased by using the moment magnifier method. And that has two parts, the non-sway part and the sway part. Non-sway is related to one column, which does not sway and only bends, small delta. And sway component is big delta, which is related to the sway of the building. And both of them have to be combined together to get the total moment magnification effect. And that magnified moment is then used to check the capacity of the section at each location. P delta analysis or moment magnification is a complicated issue because it involves nonlinear stress strain, it involves the geometric nonlinearity, change in section cracking, and so on. It involves the change of the shape of the section, geometric nonlinearity, and it involves the connection with the beam for the KL over R, K calculation. So it's a complicated procedure. And one column slenderness affects the whole structure, right? But the codes tend to simplify that into procedures that I have mentioned. All right? Any question?